In this lecture, we are going to apply the Holt-Winters exponential smoothing model in code. This is our final model for this group of models, the culmination of our study of exponential smoothing. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Let's start by importing the exponential smoothing class. Next, we're going to create an instance of our model. This time, we're not going to bother fitting a model to the entire dataset, but rather we're going to skip right away to the train test split. So the first variation we're going to try is the additive trend and additive seasonality. We set the seasonal periods to 12 since we know that the data cycles yearly and the frequency of the data is monthly. Next, we call the fit function. So let's run this. Now, due to numerical issues, we get a convergence warning. However, you'll see that the model has been fitted appropriately. Next, we assign the fitted values to the Holt-Winters column of our original data frame for the train rows. Next, we call the forecast function for end test steps and assign the result to our original data frame for the test rows. Next, we plot the Holt-Winters column, along with the original dataset. So this is very encouraging. Unlike the simple exponential smoothing model and the Holt linear trend model, this model fits very well for both train and test. Notice importantly that the predictions are not lagging behind the time series. So hopefully now you are convinced that it is not correct to shift backwards by one step, and in fact, the lagging is only due to model misspecification. Remember that you have to be consistent. If you shift back for one model, you have to shift back for all of them. And for this model, that would be very silly because then the predictions would be ahead of the data, which doesn't make any sense. Now that we know our model fits decently well, it would be a good idea to calculate some metrics. Although there are many metrics which are used in time series analysis, the root mean squared error will be just fine for us. This metric makes more sense, in my opinion, than something like the absolute error, because these models actually minimize the squared error directly. Therefore, it would make less sense to check the absolute error because we didn't optimize for that in the first place. If you're going to check the absolute error, then you may as well make the absolute error your loss function. The root mean squared error is just the square root of the squared error, which puts it on the same scale as the original data. So minimizing the mean squared error is equivalent to minimizing the root mean squared error. So here's how we calculate it. We take y, the predictions, and t, the targets, although it doesn't really matter which is which, and then we subtract them. This does an element-wise subtraction. Next, we square the result. This is also an element-wise operation. Next, we call the mean, so now we have the mean squared error. Finally, we take the square root, so we get the root mean squared error, or RMSE. Now, just out of curiosity, I would also like to calculate the mean absolute error. This calculation is a little simpler. We just take the difference between y and t, take the absolute value, and then take the mean. Hence, mean absolute error. Next, we check the RMSE on both the train and test set. As you recall, the train predictions are stored in the fitted values attribute, and the test predictions are made using the forecast function. As you can see, I've already switched around which is the prediction and which is the target, since it doesn't really matter which is y and which is t. You will get the same answer either way. Alright, so the train RMSE is about 11 something, and the test RMSE is about 15 something. When we check the mean absolute error, we get about 8 something for train and 10 something for test. Next, we're going to try the Holt-Winters model again, but with different parameters. Recall that it seems that the amplitude of the cycle increases with the level of the time series. This suggests that a multiplicative model may fit better. So for this model, we're going to have an additive trend and a multiplicative seasonality. Again, we call fit, assign the train predictions and the test predictions to the data frame, and then plot the result. So we're just doing it all in one step since you already know how each of these steps works. So from my perspective at least, this model appears to fit better than the purely additive model. But let's check our accuracy metrics. So when we check the RMSE, we get about 10 something for the train set and a 17 something for the test set. This is a better train error than the purely additive model, but the test error is worse. Therefore, we would not want to choose this model. If we check the mean absolute error, we see the same thing. The train error is better, but the test error is worse. Next, let's try Holt-Winters again, but with a multiplicative trend and a multiplicative seasonality. This kind of makes sense because the trend in the time series is not exactly a straight line. The growth actually seems to be accelerating over time. Again, we call fit, assign the predictions to our data frame, and plot the result. It's difficult to tell whether this is a better or a worse fit, so let's check our accuracy metrics. Alright, so here we see an interesting pattern. The train RMSE is about 9 something, and the test RMSE is about 25 something. So the train error is better, but the test error is much worse. We see the same thing for the mean absolute error. The train error has gone down, but the test error has gone up to about 20 something. Therefore, while this time series may look like a multiplicative model is a better fit, it actually overfits to the training data, and we get a worse result.